Hello everyone. In this lecture, we'll be looking at the dynamics of capillary rise. We'll start with something that all of you already know, which is the static case. In capillary statics, we've seen that when we dip a capillary tube into a fluid bath, then the fluid would rise to a certain height, as shown here schematically as with the variable h. The height to which the fluid rises depends on the surface tension, the contact angle that the fluid meniscus makes with the tube, density, gravity, and the diameter or the radius of the tube. Now, what we want to do in today's lecture is to basically take this one step further and ask, what is the process in which the fluid would rise in the meniscus? Meaning, we want to derive an evolutionary equation for the capillary rise as a function of time. Now, there are a bunch of parameters which are relevant. We've already seen a bunch of them already here, which is gamma, the surface tension. A is the radius of the tube. Rho is density. G is gravity. And theta is the contact angle. Now, because we will be dealing with dynamics, an additional parameter which will come in, which is the resistance offered by the fluid to flow, then that is viscosity. This is a new dynamic parameter that we will introduce into the analysis, and we'll be looking at evolution equation. Now, the static problem is something that can be easily checked in an experiment. So here's a fluid that is rising in a capillary tube, and you can see that the final height can be clearly seen. But what we also want to do is to study the dynamic problem, and this is a small movie indicating how the fluid actually is rising. And notice that during this evolution process, the contact angle does not really change much. So that's an important assumption that we'll be making. So assumptions that we'll be making are theta, gamma, which is surface tension, and viscosity, they're all constant. We are ignoring more complicated aspects such as evaporation. When we say theta is constant, the surface tension force also remains constant, and the radius is also constant, therefore it's a rigid tube. We'll also be making a few other assumptions, but these are the important assumptions, and when I introduce more assumptions, I will discuss them. So the goal of the lecture is to determine an evolution equation for this z of t as shown as in this particular schematic. Let's look at the force balance on the fluid. So to write down the force balance, we will first look at what are the common forces that are at play. Forces at play, we can basically separate the forces into two parts. So first I'll call as the driving force. And there's only one driving force, which is surface tension. And then we have a bunch of opposing forces. Opposing or retarding forces. Now, these include gravity. The weight of the column tends to pull it down, which is an opposing force. We have a retarding force, which is a viscous force, which tends to slow down the motion of the column as it rises up. Then we have dynamic pressure. We'll look at it more closely, but the general idea is that when a fluid is moving through with a certain velocity, then the pressure is actually lower because of Bernoulli's equation, and that tends to pull the fluid back, and therefore it appears as a retarding force or an opposing force. And finally, we have inertia. So the more heavy the fluid is, more amount of force you would need to pull it up. So these are the four forces. Now let's look at the force balance on a column. So for that, I will start by basically drawing a small column. So here's a capillary tube that is shown here. And in this capillary tube, the fluid has risen to some particular height. This is not necessarily the final height. And I want to take a small control volume. I want to write down the force balance for this control volume. So let's write that down. The forces, the force balance involves the standard Newton's second law. We will write down, we'll use the conservation of momentum. So we have d by dt times m of t times z dot. Z dot is basically the how the position is changing with time, would be equal to sum of all the total forces plus any flux that is entering this is the force balance. Okay, this is just coming from conservation of momentum. So the idea is that on the left hand side we have mass times acceleration, the inertial terms. We'll also have a new term which is the added mass term. On the right hand side, the sum of forces would involve forces like surface tension, gravity, viscous forces, dynamic pressure, and so on. Now this last term that you see here is basically the total momentum flux and the left hand side that you see here is the rate of change of momentum in the control volume. Now I have to make a small comment about the velocity v and z. What's the connection between velocity v and z dot? Okay. Now let's say basically at any point we'll be making another important assumption, which will be assuming that the flow is fully developed. This is not true initially because of boundary layer effect, but once the flow has reached a fully developed state, then you can expect a parabolic velocity profile, and we can easily write down the velocity profile for this case, which is that the vertical velocity, if I call it as u, then it is changing with the radius, where we are looking at a tube at any point r. The radius would just be 2z dot 1 minus r square by a square, where z dot is basically an average velocity. So now I can say z dot is an average velocity, which we'll call it as v. Alright. Now we want to write down the force balance on this control volume, but I already said that we will be making the fully developed condition. Now let's look at why is a fully developed condition valid. And for this, let's go back and take a look at what's likely to happen in this, what is happening in this column. So we look at the entrance region of this column. In the entrance region of this column, the fluid is entering practically with a constant velocity. But then, after a certain distance it has traveled in the tube, it has reached a fully developed state. Now there is a time scale associated with this process. How do we get the time scale? If I were to write down that, if I say that the boundary layer is basically going by diffusion process, then the time scale would be density times del u by del t. Basically this is the local acceleration, would be, so these are the dominant terms. Okay, and we now have, if u is the velocity, And if the menace fluid is rising, then a typical estimate for this would be T by, we'll call it as time as T mu, which we want to find out what is this T mu, which goes as mu u dot by a square. And this gives me an estimate for T mu, which is a square by nu. A is the radius of the tube, and nu is the kinematic viscosity. So for example, if A is taken to be, you can take a typical number. If A is 0.1 mm, and if you use water as a fluid, then kinematic viscosity for water would be 10 power minus 6 meter square per second. This is for water. Then the estimate for mu would be something like 0.01 seconds. So what I'm trying to convey is that if the tube is very thin, then you would expect a fully developed state to be achieved practically instantaneously. So a fully developed state assumption is a fairly good assumption. Now one can easily calculate what would be the typical value of mu for slightly thicker diameter or thicker radii tubes. If A is 0.5 mm, you'll see that T mu is 0.25 seconds. Okay, so it's basically quite small. And once I know the velocity profile, I can actually calculate something like the shear stress. The shear stress in this case would be del U by del R at R equals A, and this would be Z dot. Okay, and this shear stress will be relevant when I write down all the workout, all the forces. So let's write down the force balance for this system. The force balance in this case would be whatever I've written down earlier, which is mass times acceleration on the left hand side, would be sum of all the forces. So let's write that down. You can call it force balance or you can call it conservation of momentum. Now conservation of momentum leads to, this is a force balance on the column that I've shown here in this red dashed region. That's the control volume. The force balance in this case would be mass. There are two masses, and it will become clear in a minute why that's the case. You have two masses times Z double dot would be 2. Let's write down the driving force. Gravitational force is opposing. Viscous force is also opposing. And finally, we have a dynamic pressure, which is also opposing. Let's look at each of them. So let's start with surface tension force. This would act all along the column at the meniscus. And if I basically think of it like a force, this is gamma, and the angle is theta. It's acting all along the perimeter. That's the contact line. And therefore, the driving force in this case would be 2 pi A, that's the perimeter, times gamma cos theta. So we are interested in the unbalanced force is the vertical force. Okay. Now, let's look at gravity. Gravitational force is also nothing but the weight of the column. The weight of the column would be mg, and what is m here? This is the mass of the column. So it will be pi a square will be the area times z, that will be the height of the column, multiplied by density. That's the mass of the column. The dynamic pressure I've called it as FP. That will be pressure times area, half rho V square. That's basically the pressure times area. And pressure would be by Bernoulli's half rho V square. At any point, the column is rising with a velocity of z dot square times area. Now one can easily understand why this term would enter. In the initial stages, when the fluid is rising with almost like an inviscid flow, because the boundary layer is very thin, when the fluid is rising with a velocity of z dot, then when it is rising with a z dot, if I apply Bernoulli's equation, the pressure would be lower in that region. So at the entrance region, the pressure will be lower, and this provides some kind of a reverse suction force which tries to pull the column back. So that's basically the dynamic pressure. And finally, we have viscous force. And the viscous force, F mu, would be the surface area of the column. The surface area of the column would be the height of the column multiplied by the perimeter circumference. That will be 2 pi a times z, okay, multiplied by the shear stress all along. The shear stress, which we'll call it as tau mu. That's basically my viscous force. Okay. So now that I have all these terms, we can write down the equation, which is the force balance, which is M plus MA Z double dot would be 2 pi A gamma cos theta, that's a surface tension force, minus pi A square Z times rho, minus half rho Z dot square pi A square, minus 2 pi A Z tau mu. Right? So now that we have this, we want to determine the added mass. And this is mass here. And also remember that Z here, Z is function of time. Z and Z dot are both functions of time. Okay. So left hand side clearly is like are the inertial terms, and the right hand side are all the forces, driving forces as well as opposing forces. Okay. Now to determine the added mass, I will basically closely follow the approach taken by Professor John Bush. So Professor John Bush has a very nice lecture notes on a course called Interfacial Phenomena. So this part of the material, it closely follows his lecture notes. So let's look at the added mass as well. But before this, let's try and do one interesting thing, which is let's make a guess for what will be the shape of this curve. If I were to determine the added mass, then I have a nonlinear equation for z of t. And if I were to solve this nonlinear equation for z of t, what will be the shape that I get? But before we actually derive the governing equation in full, let's first make a guess of what the shape would look like. Now our goal is to basically get this curve, how z of t varies with t. Now there are a few things that we know for sure. At t equal to 0, that's the definition of time for me in the start of the experiment. We know that the fluid in the column starts at z equals 0. That's the green dot at the bottom. I also know that when the fluid at very long time, the fluid will eventually reach a final height, which basically this is z is equal to h. That's the final height given by the Jordan's law. So the fluid has to go from here to that height. Now, how does this happen? Now, it's a reasonable guess to say that when it starts, the velocity is very small because the position is small. The velocity is also very small, but the fluid is basically being pulled by an unbalanced force, which is the surface tension force. The surface tension force immediately starts acting, but the other forces, primarily the gravitational force and viscous forces, are very small. Therefore, you should expect that the fluid rises at a constant acceleration, and constant acceleration would mean that the curve would be something like this. The reason for this is because here, if you say acceleration is z dot, if it's constant, then it means that the velocity z, this goes like t, z dot goes like t, and z goes like t square. So basically it's a parabolic shape. You should also expect that at very large time, the fluid would basically approach a constant value and it would decay to the final Jordan's height. And somewhere in the middle, you should expect that after an initial acceleration, you should expect that the forces are now in balance. And once the forces are in balance, the sum of forces is equal to 0, and therefore you should expect that the fluid starts moving with a constant velocity. If the fluid is moving at a constant velocity, the curve that you should expect in somewhere in the middle would be linear, because in this region, z double dot is approximately 0. That's acceleration is very small. Z dot is constant, and therefore z goes like t. Therefore, z goes like t. Now it has to somehow connect from here to that decaying state. The final decaying state would be some kind of an exponential decay. We'll look at this later, but you should expect that this linear region somehow should match to that exponential decay. So there has to be some tapering that has to happen. So maybe this goes like z goes like t power alpha, where alpha is less than 1, meaning it's growing less slowly than a linear stage. Okay, so this is sort of the guess that we can make even before we solve this. Therefore, you can actually say that this region, the first region here, is inertia dominated, these two regions, and this is viscous dominated. Note that surface tension is present throughout. So you're going from an inertia dominated region where inertia becomes less and less and less important because the fluid is slowing down, and then you enter a viscous dominated region. And viscous dominated region, again, you can sort of divide them into two parts. I've shown them in black and green curves. So we will look at each of those regions. But let's look at the force balance. We've already written down the force balance. We have to write down the added mass now. Our goal is to calculate the value of this MA. So for that, I've shown a schematic here. So the fluid is rising in the column with a velocity given by v dot. And what we want to do is we want to ask, as the following question: as the fluid rises from a height of z to z plus delta z with a velocity v, we want to ask how much of kinetic energy is being imparted to the body of fluid that is below. Therefore, I can basically divide this, the forces, into three parts. Okay, Let me write that down. We estimate the added mass by determining the change in the kinetic energy as the column rises from Z to Z plus delta Z. So the change in kinetic energy, let's call it as delta Ek. Let's say this is the change in half m some u square. Let's determine basically what is this m here. The m can be divided into three parts. So m is, the first part is, I can say m is nothing but mc, that's the mass in the column. Then I have m naught, that's the mass in the spherical cap. So in the process, we will look at the schematic to the right. When the fluid is rising, it is basically generating kinetic energy into the fluid. So we can say this is m naught, and this is mass in the spherical cap. And then finally, we have m infinity. Okay, mass in the container. Okay, let's write down each of those terms. Mass in the column, we've already seen this, pi a square z times density. Okay, and for this case, the velocity u will be capital U. That's the fluid, the rate at which the fluid is rising. Mass in the spherical cap, you can say, is it's basically a spherical cap, therefore it is half the volume of a sphere, that's 2 by 3 pi a cube, and the fluid is rho, and the velocity is again capital U. So the balance that we have, force balance that the mass balance that we are looking at is we have a spherical cap here, and in the spherical cap, the fluid is basically going with the velocity u. And because the fluid is going with the velocity u, it has to enter with some velocity. Okay. So therefore, I can write down by conservation of mass, I can write down rho pi a square. That's the fluid that is leaving the spherical cap. That is capital U that I've already shown here in blue here. Rho pi a square times U should be equal to basically mass that is entering the spherical cap. And the mass that is entering the spherical cap would be the surface area of the spherical cap, 2 pi a square times UR at A. So we are interested in looking at a spherical cap whose radius is A. Okay, and therefore I can say UR at A is just nothing but U by 2. Therefore I can now say the velocity at the inlet of the spherical cap is capital U by 2. Fluid is entering the spherical cap at U by 2. Okay. Now we can take this one step further and ask, if I have a spherical cap this way, I can go one step further and ask, if I have a bigger region at a distance of small r, I could ask, what is the radius, what is the velocity that is entering this region? We're making an assumption that the fluid is entering in a spherically symmetric fashion. So we want to determine what is the size of this green arrow. Okay. So with the same argument, two pi a square ur at r equals a, this will be equal to 2 pi r square ur at some radius r. And therefore I have the radial velocity at some radius r will be a square by r square times ur at r equals a. But we've already determined the velocity at r equals a. That is the spherical cap shown in the blue arrows. And this, if I substitute that, I have ur at any r will be a square capital U by 2r square. In other words, if fluid is entering the capillary tube with a velocity of capital U, then the fluid at some distance r in the body of fluid below the capillary tube, to a good approximation, would basically decay like 1 by r square. Okay. So now I can write down the kinetic energy in the far field. This I can write it down as half. I basically integrate over the whole volume dm ur of r whole square. Okay. And in this case, I'm going from a to infinity. So in other words, I'm going from the edge of the spherical cap. So I keep saying spherical cap. So this is my spherical cap. And the mass that is contained in the spherical cap is m naught. Okay. So from the edge of the spherical cap all the way to infinity, I'm basically calculating what is the total kinetic energy. Okay. And so this I can approximate this, instead of writing it as an integral like this, I'll just say this is some m far field, some effective mass times velocity. Okay. And we can easily calculate this. M infinity, this effective mass times u square, a to infinity, dm u of r at r, some radius whole square. So in other words, I'm doing the following integral. This is at some r. I have a spherical cap region here. This is at r equals a. And I'm basically taking a small radial region of thickness dr. So I'm going from I'm taking a small spherical region of dr, and then basically it's a spherical shell, and I'm integrating it from a to infinity. Okay, let's do this integration. This will give me m effective infinity 1 by u square. The half gets cancelled. A to infinity. So I have a square by 2r square of capital U whole square times density times 2 pi r square dr. Okay, so once I have this, I can do this integration, and you can easily verify that this integral will give me a value half rho pi a cube. I would like all of you to try out this integration on your own. So that gives me effective mass as rho pi a cube. Why do we get a finite value? Because it says that even though I'm basically generating kinetic energy in the body of fluid below the capillary tube, the velocity that I'm giving is a decaying velocity field, and we are replacing this decaying velocity field like an effective mass. It's as if I'm basically taking a mass whose value is half rho pi a cube and giving it a velocity of u. In other words, the kinetic energy would be half rho pi a cube, that is m effective, that times half mv square, half mu square. That's the kinetic energy. Okay. Now, therefore, I can now say change in the kinetic energy delta Ek would be mc plus m naught plus m infinity. This m infinity is m infinity effective. That's basically, remember, we wrote down delta Ek is half. The expression for delta Ek that we wrote down was delta of half mu square. So this change in kinetic energy can occur because of change in the velocity and also because of change in mass. So this is the first term accounts for change in mass, and the second term accounts for change in the velocity, half m 2u delta u. Okay, let's substitute each of them. Half delta mc u square plus half delta m naught times u square plus half delta m infinity times u square plus half m naught plus m column plus m infinity of 2u delta u. That's my expression that I have here. And this gives me, now there are a couple of things to note here. The amount of mass that inside the column is changing as the fluid is rising in the column. Okay, so the first term is clearly non-zero. The second and the third term, delta m naught, is constant because the spherical cap, whatever mass is entering, is also leaving into the column. The same is true for delta m infinity, which is because we're saying it's a very large body of reservoir. So even if a little amount of mass is going into the capillary tube, the change in the mass in the reservoir is very small. So therefore, I can basically say these two terms are practically zero. Okay, I can also cancel the 2 here, and let's do the simplification here. The first term would be the change in the mass in the column would be because of the change in Z. Then I have m naught on the right hand side, that's pi a square rho Z. mc, the mass in the column would be pi a square m naught rho Z. M naught would be 2 by 3 pi a cube rho, and we calculated m effective or m infinity, and m infinity in this case would be half rho pi a cube. That's what we have, and this is u times delta u. Okay, so this quantity here that we have here, this is delta Ek. Okay, and this quantity, the first term that you see here, let's simplify this a little bit and then we'll understand what each of these terms mean. This is rho pi a square delta z times u square. Then we can group some of these terms here. So I have rho pi a square times z plus 7 by 6a times u delta u. Okay. So I would like you to try and verify this yourself. So I can interpret each of them. This is change in kinetic energy only due to column. And this quantity can be thought of as contribution, this entire quantity by the way, contribution from all the mass that is being dragged along, from the reservoir below. Okay. So now you can clearly see that there's an additional term that has come into place. Okay. If I did not have a reservoir at all, okay, if I did not have a reservoir, then essentially or maybe the statement should be, without considering the reservoir effect, now we have taken the case of reservoir into this calculation. This is delta Ek. Okay. Now let's consider the case without considering the reservoir below. Without considering the reservoir below, what I would have got the kinetic energy, change in the kinetic energy would be half m mu square. And this quantity would be half delta m u square plus half m of 2u delta u. That's because of the change in the second term. And I can clearly write down the first term would be the change in the, if I do not consider the reservoir, I only have the column. So that's density times pi a square delta z times u square. And then I have half m then I have half m. M is nothing but density times pi a square z times 2u delta u. Okay. So now let's compare these two expressions that we've got here. So this is the second term that I've got here. This is without reservoir. Whereas the expression that I have below has the reservoir effect. Okay. Right. So what do we conclude from this? You see here, if I take the reservoir into account, I get an additional contribution of the 7 by 6a term. Okay. So I can conclude, comparing the two expressions, so I'm comparing expression 1 and expression 2. So that is 1 and 2. If I were to compare these two expressions, we can conclude that the effective added mass term is MA, that's added mass, rho pi A square times 7 by 6A. That's the added mass, additional added mass effect that I've got. Okay. So now I can substitute it into the force balance. So which is the force balance that I want to get into? I've written down the force balance here. I know M, I know MA, and I have all the other terms. Okay. Now let's call this equation a star. And I want to substitute my added mass term into that star. Okay. We have mass, that is rho pi A square Z, plus the added mass, that is rho times 7 by 6 pi A square pi A cube Z double dot. This will be equal to sum of all the forces. The surface tension force 2 pi gamma A cos theta. Then I have weight. Then I have viscous force. So if you remember, I've already derived the viscous force here, tau mu, but there's one important thing to remember. The tau mu has appeared with a negative sign, or tau nu has appeared with a negative sign, but I have not taken that negative sign into account because when I wrote down the force balance, I already wrote down the force balance with the viscous force, assuming that the viscous force is a retarding force. Therefore, I've already taken down the minus sign. If I were to again substitute in the expression for F mu, if I were to substitute in this value here, tau mu, if I were to substitute a negative sign, then I would be taking 2 times negative sign, and that would be incorrect. Okay. So that's my viscous force. And finally, I have the dynamic pressure term, that is half pi A square rho Z dot square. Okay. Now we can divide throughout by rho pi A square. We get, what's the expression we get? Z plus 7 by 6A. This is Z double dot. This will be equal to 2 gamma cos theta by rho A minus GZ minus 8 mu Z dot by rho A square. Finally, I have Z dot square by 2. I would like all of you to carefully try and do this yourself and verify that this expression that I've written down is correct. Now, this is a very important result. We have to remember that Z is nothing but Z of t. Z dot is nothing but dz by dt. And Z double dot is d square Z by dt square. Now, what kind of an equation is this? This is a nonlinear ordinary differential equation for the Z of t. So if I know two initial conditions, which is because the second order nonlinear ordinaries, I can say second order ordinary differential equation. Okay. Now, if I require two initial conditions to solve this equation. So typical initial condition would be to say that at t equal to 0, Z is 0. And the other initial condition would be at t equal to 0, z dot is also 0, which means that the fluid is rising with a constant velocity. Now in the next lecture, what we'll be doing is we'll be analyzing this equation in detail. This equation directly cannot be solved because it's a nonlinear equation. But what we will be doing is to look at various regimes in this process. Now the regimes, remember, is something that we've already sort of made a guess here. We have inertial dominated regimes and viscous dominated regimes. So we'll split this equation into different regimes and see, does it give us more insight? Okay, and does it agree with what we've already obtained with the guess that we've made at the beginning of this lecture? So I hope you join me for the next lecture as well. Thank you.